Alright, this is 3.3 homework. This set is a little smaller, so I'll be going a little more in depth into everything. But again, feel free to message me on Discord or email me, whatever. So, first one, 75. Two isomers of the planar compound 1,2-dichloroethylene are shown here. This problem is kind of fun because this is like the type of stuff I'm doing organic, but anyway. Which of the two isomers will have the stronger dipole-dipole forces? So I drew both of them up here. So this is the cis isomer, and by the way, cis means same, and trans means different. So I guess change. So here with the cis, both of the CLs are at the bottom, while in trans the CL is up here and down here. So they're kind of across from each other. Uh, so for multiple reasons, the trans isomer is more stable because the CL. Sorry, I'm not going to tangent, but this is more stable because the CLs are away from each other, causing less forces to hit each other. So in general, in chemistry, you'll see trans isomers instead of cis isomers. But anyway, uh, I would say that the cis isomer has stronger dipole-dipole forces because if you look at the cis isomer, all of the negative charge or most of the negative dipole is focused down here in the bottom where there are CLs, while the hydrogens, which would still have, it's more covalent, it's less electronegative, where the electrons are more evenly split. So that means that we're going to generally see a positive minus split where it's going to be pretty polar. And then with trans isomer, uh, it's not going to be the same story because this it's split evenly. Where if you it has multiple planes of symmetry, so that it is non-polar. Generally, it's still a little polar, but it's considered non-polar as a molecule. So the isomers with stronger dipole-dipole forces is the cis isomer because it benefits from having dipole-dipole forces because it is polar. Uh, and then for B, one isomer has a boiling point of 60.3 degrees Celsius and the other 47.5 degrees Celsius. Which isomer has which boiling point? Well, we went over this. The molecule with the strong intermolecular forces will have the higher boiling point, so it will be the cis isomer, and the trans isomer will boil at 47.5 degrees Celsius. Alright, 84. So, quick disclaimer, this equation that shows, like in this question, does not show up on the AP exam. At least it did not show up on my AP exam. I didn't hear about anything getting added to AP Chem, at least for the 2023 exam. So I would say this is a pretty low priority question, but it's homework, so you should still do it. So for A, it's asking me or us to find the relationship between vapor pressure and the absolute temperature. So for that, I just simplified out the equation to get ln of P and ln of P2, and I just put this equation right here. I checked the the answer key for the textbook, and that's what it says. So I think I'm right. I don't know what else you could do. Although you could go all the way and just completely isolate P and do like E of ln of P1, and then solve for P1. You could do that, but I don't know. That's a lot of work. And then for B, C, and D, you are plugging numbers into the equation. So for that reason, I didn't show work for every single part because that'd be kind of unnecessary. So I'll just plugging. So for B, I showed the work. I wrote out what was given. So the initial pressure and then the final pressure, the initial temperature and the final temperature, and solve for enthalpy. And with that, I got 40 kilojoules. And then from there, I just plugged in, like I did the same thing for C and D, and you have to use your answer for A for B, and you have to use your answer from B for C. So make sure to do that on your problems. So for A, I got 40 kilojoules per mole. For for B, I got 40 kilojoules per mole. For C, I got 395 Kelvin for temperature 2. And for D, I got 0.35 torr. And if you get stuck on these problems, don't be afraid to ask me. I can show you my work. Alright, 77. When an atom or group of atoms is substituted for an H atom in benzene, the boiling point changes. Explain the order of the following boiling points. So let's just preface that, first of all, benzene, which is this molecule, is a non-polar molecule. So in its base form, without anything, it is just a simple non-polar molecule with only LDF forces. It's a small molecule at that, so it doesn't have very strong intermolecular forces. It's actually weaker than water. So yeah. So when you add anything to it, it'll shift the balance. Like for example, with uh, C6H5Cl, or I think one one chlorobenzene or one chloro sure. Uh, it'll make this molecule polar, give it a negative and positive side, where it'll increase the boiling point by adding dipole-dipole forces and also stronger LDF forces because you're adding a bigger atom. So this also applies to Br, where bromine, where since bromine's a larger atom, the first of all the polarity is going to be even starker, and um, the LDF forces will be even stronger. And then this finally ends with OH being the strongest, with OH having hydrogen bonding, which is the strongest intermolecular force. Therefore, it's going to have the highest boiling point. So that's the answer for 77. A lot of reasoning. All right, for 78, the DNA double helix at the atomic level looks like a twisted ladder where the rungs of that ladder consist of molecules that are hydrogen bonded together. Sugar and phosphate groups make up the sides of the ladder. Shown are the structures of the AT base pair and the GC base pair. So you can see that the AT base pairs are more stable. Sorry, you can see that they're held up by 2 hydrogen bonds, and the GC pair is held together by 3 hydrogen bonds, which is more stable to heating. So since the GC pair has hydrogen bonds with the OH, it has more hydrogen bonds, sorry, it is more stable to heating. So that makes it have a higher boiling point so that it doesn't break up as easily. If you heat up the AT pair or the adenine thymine pair, it's gonna break more easily because there's less OH, there's less of those stronger bonds. Because hydrogen bonds are pretty strong, so therefore the GC bond will be more tolerant or I guess stable to heating. Okay, acetone is widely used as an industrial solvent. A. Draw the Lewis structure for the acetone molecule and predict the geometry. So this should be a review for you because this is last unit. But this is the Lewis structure. Don't be fooled by the CO, thinking it's like a weird thing. The CO is in the middle. It's just that it's it's more electronegative, so it's gonna be the middle. It's gonna be the donor. Anyway, the geometry around the central carbon atom is trigonal planar, and so this is trigonal planar because it's just 3 planar bonds. And then with the other 2 carbons, it's gonna be tetrahedral because there's 4. And then for B, is the acid molecule polar or nonpolar? It's pretty obviously polar because there's this massive oxygen here creating a negative charge. Although it's not like super polar, it is polar. And then for C, what kind of intermolecular attractive forces exist? There's going to be dipole-dipole as it is polar, although they're a little weak, but they still exist. And LDF forces, which is just in every molecule. Finally, D, 1-propanol has a molecular weight that is very similar, yet acetone boils at 56.5 degrees Celsius, and propanol boils at 97.2 degrees Celsius. So, propanol looks like, 1, 2, 3, it looks like this, I think. No, it looks like this. So, as you can see, propanol has a OH bond, which has hydrogen bonding, which greatly increases its boiling point. Furthermore, it has the weird shape. It has the flat shape, which makes it easy to stack on, giving it a higher boiling point. While acetone has this weirder shape, which is this, which is harder to stack, therefore making the boiling point lower, making less energy. So overall, for a lot of reasons, propanol has a has a higher boiling point because of its stronger intermolecular forces, because of its hydrogen bonding, and because of its shape. Okay, 90, last problem. The table shown here lists the molar heats of vaporization for several compounds. Use examples from the list to illustrate how the heat of vaporization varies with, and some examples. So, starting with A, and also I drew the molecular shapes of each of the molecules. Anyway, for A, so for molar mass, this is best demonstrated by molecules 1 and 2 because they both have the same structure and like general shape, and they're both nonpolar, so they're kind of like the same thing. It's just that 2 has a longer chain. In fact, it's double. That gives it a higher heat of vaporization because it has much stronger London dispersion forces or LDF forces, and that gives it a higher heat of vaporization. And then for B, the reason why 3 and 4 have a different molecular shape, where 3 has kind of a weird shape, and I'll kind of draw it a bit bigger. It's this. So the reason why that makes it a much lower heat of vaporization is because it's a weird shape, so things can't really stack onto it. Like the intermolecular forces drawing them together isn't going to be as strong because of the weird and awkward shape of the molecule. This leads to 3 having a lower having a lower heat of vaporization than 4 because of its shape. And then with C, molecular polarity. So the polar bonds, like in 3, 4, and 5, no, 1, 2, and 4, 5, and 6, those all have polar bonds. Actually, no, 3 has them too. 3, 4, 5, and 6 have polar bonds, and as you can see, they all have a higher heat of vaporization than 1 and 2, which are nonpolar. So, given that these bonds that are polar have higher heat of vaporization on average, that means that the molecular polarity kind of correlates there. And then lastly, hydrogen bonding. Hydrogen bonds, the only molecule on here, 6, that has hydrogen bonding, it has the highest heat of vaporization. So the hydrogen bonding increases the intermolecular forces, leading to more energy being needed to break them apart and vaporize, or I guess evaporate. So that's the reason why. And that's all. Have a great day and enjoy chemistry, I guess.